I am Talya Mehmet Esenzaide from SPBOCS team. Today I will be your moderator during the session. So this is the last week of the process engineering course, and today's lesson will be with Sanan Süleymanlı. He will share his experience. And now stage is yours. When you have any questions, you can write to the chat box or just unmute yourself and ask your question. So Sanan Bey, you can start.
Thank you, Talya Hanım, for the introduction. I would like to greet all of you. Thank you for joining this session. Last week we had not last week. Yeah, on Sunday we had the first session of the oil refinery processes course, where we talked about the oil refining, why we are refining the oil, what are the outcomes, what is the view and the block flow diagram of the oil refinery. And I gave an assignment which was about to learn the processes in general, but not memorize, but to understand why block flow diagram looks like that. Now I would like to share my screen, but before I started, I told Katya Hanım that today there will be a quiz, which will be the end of our sessions. But later I thought that if I try to finalize the sessions today, that would be too intense for today. That's why we will probably have one more session, and that will be, we can discuss, that will be on Sunday. At the end of the session, we will have a quiz, which will be the questions will be today's session and Sunday's session. And for the highest score, I want to promise a surprise gift, which will be from Sokar. That's why be careful. Listen carefully, ask your questions, take notes during the session. If you have any questions, please do not hesitate to bother me. Ask your questions. You can ask your questions with just speaking or writing your messages in the chat box. Let me share my presentation. So this is the how oil refinery looks like, and this is not just a plant, this is a complex. And so what we said in the previous session, that the oil refinery consists of different units. Now I've made a squares here. Each square is kind of one unit. This is one unit, this is one unit, this is one unit or two units, and there are some other units in this area. So now I will show you the block flow diagram, which you already saw that. So each the square in the block diagram is a unit, and each unit has all different types of equipment, such as pumps, compressors, columns, the reactors, furnaces, heaters, heat exchangers, etc. So one unit can consist of between the 50 or 500 pieces of equipment. This is what is the unit when we say in the refinery. So I would like to again show this slide, that how engineers learn. Engineers do not memorize, they think, they analyze, they understand, and this is how they learn. This takes longer than memorizing, but in fact this lasts longer. And after you learn, you repeat what you learned. For instance, you take notes and you repeat your notes, you reproduce, maybe doing the assignments, and teach others. When you teach others, you must learn here. And if you do all of them, then you remember. So as I told you in the first session, that I used the petroleum refining complete guide to products and process course on Udemy. I mostly use the presentation slides, and I added some slides from the reference book I used. This is the oil refinery block flow diagram that we discussed during the last session. Now I would like to summarize it briefly, because it is really important to understand the processes in the BFD first, and then we go the one by one each unit. So this is, where is it? Yeah, this is one unit. Gas processing, another unit. Amine treating, another unit. The lead coker, this is another unit. So these are the main refinery units. This is CDU. This is VDU. One moment, why it is so small? Okay, I couldn't make it thicker. And we have VDU, this is VDU. Fluid catalytic cracking unit, this is FCC. Can you see my writing, my notes?
Yes, Sanambe, we can see it.
Okay. And continuous catalytic reforming unit, this is CCR. Here we have CCR. The naphtha hydrotreating unit. So we have the hydrotreater, this is NHD. We have different hydrotreaters. This is the NHD, naphtha hydrotreater. We have DHD, which is the diesel hydrotreater, and we have, no, this is not FCC, sorry. FCC is this one. This is, we called it VGO. So you can see it is vacuum gas oil mix of light and heavy VGO. That's why we called it VGO HD, VGO hydrotreater. And naphtha splitter actually splits light naphtha and splits light naphtha and heavy naphtha. And then we have the isomerization unit, which is this one. And we have the bitumen blowing unit. Here we have the BBU to produce the bitumen and the late coker unit to produce cokes. Okay, let's go one by one quickly to understand the block flow diagram. Who attended the first session, that will be easier for you, that will be repetition for you. Who is the first time in the refinery oil refinery processing course, please listen carefully and try to understand why we have the atmospheric distillation unit, which is today's main topic, to separate the products related to their boiling points. As you can see, we have the gases here, which are C1, C4. We have light naphtha and heavy naphtha. Light naphtha is C5, C8, and heavy naphtha C10, C12. And then we have the jet fuel or kerosene, which is the C12 to 18. Diesel, the C20, the C30, then atmospheric gas oil. Or we can also call it AR, atmospheric residue. Atmospheric residue. Sorry.
Excuse me, can I ask a question?
Yes, sure.
We call them as atmospheric because it goes out at atmospheric pressure, or there is another reason?
Yes, exactly. So here the pressure is around the 1 bar G or 1 atm gauge pressure. And when it comes to here, the pressure is around, let's say 30, 50 millimeter mercury. So as you know, 1 atm is 760 mmHg. In this case, the 50 is around 0.05 bar G. And we will talk about this later in details, because today we will learn the CDU and VDU. We will talk about these units mostly. That's why we will talk about the pressure, temperatures, and the equipment in these units further. So this is the atmospheric bottoms or atmospheric residue. which is further separated to light vacuum gas oil, heavy vacuum gas oil. Sometimes we also have here diesel, which is sent here. So the aim of the CDU and VDU is to separate the products based on their boiling point. Finally, we have the vacuum residue, and it is sent to the coker unit to produce coke or bitumen, asphalt. So asphalt is our one product, coke another product. When we have these products separated, now they have to be treated. Why? Because they have the high amount of sulfur content mostly, and also the nitrogen content. These impurities should be treated. That's why we have the hydrotreaters for each product. And then we send light naphtha to isomerization, heavy naphtha to catalytic reformer. Here we produce the aromatics. Here we produce the isomerate. Why we do that? Because the isomerate has higher octane number than light naphtha, and reformate has higher octane number than heavy naphtha. Then all the isomerate reformate are sent to gasoline blending pool. It's a gas processing plant. We have the gases from C1 to C4. What we do, we treat them, we clean the sulfur in gases, and also we split them to C1 and C2, which is dry gas, C3, which is called the propane-propylene fraction, and C4, which is called the butane-butylene fraction. And we have other gases here. What are other gases? Gases from FCC, gas from catalytic reformer, gas from hydrotreating, gas from isomerization plant, gas from hydrotreater, gas, and gas. All the gases in refinery are collected in one gas processing, let's say, unit. There we split it to dry gas, PPF and BBF, and we treat them, we clean them. Dry gas is used as fuel in the refinery, and PPF and BBF are sent to sales. When we treat H2S in the dry gas, we absorb H2S with amine treating, and H2S is sent to the closed sulfur plant, or you can call like sulfur recovery unit, where we produce sulfur. And then you can ask why we have the FCC. We will talk about FCC in detail in the next session. In FCC, we crack the higher hydrocarbons with higher carbon chain, 20 or 30, to lower ones. Why? To produce the more gasoline. This is the FCC. We produce gasoline. You can see naphtha, it is hydrotreated and sent to FCC gasoline, to gasoline pool. So this hydrotreater will be called GHT, for instance. Why? Gasoline hydrotreater. And then we have the FCC gas oil. This is diesel. And that's all. We have also sometimes we call it the slurry, which is the really heavy fraction. Slurry is sent to the lead coker unit. This is the BFD in general. I spoke about it quickly because we went over this BFD one by one in the previous session. If you didn't attend that one, you can ask for the recording and watch it. Now I would like to continue. If you have any question, please ask. Okay, just as side information, these are the main units, but we have also some auxiliary refinery units, which are the hydrogen production units. Why we need hydrogen? Because hydrotreating means that treating with hydrogen. For these units, we need hydrogen. You can see hydrogen here. You can see hydrogen. And this hydrogen comes from catalytic reformer. Here, we produce hydrogen. But this hydrogen is not enough. That's why we have additional hydrogen production unit, which is shown here. This is HPU, hydrogen production unit, where we use the natural gas and steam to produce hydrogen. We have the pressure swing adsorption. Why we need this one? To produce the high purity hydrogen. So you can assume like that. We have low purity hydrogen to swing adsorption block, pressure swing adsorption, where other gases in hydrogen is adsorbed, and then we produce high purity hydrogen. This is around 99.9%. This can be around 84%. Then we have the sulfur recovery, which I talked about. We have sour water stripping wind. What is that? The water, sour water. What is sour? Means that high H2S content is sent to SWS. What is stripping? Just kind of evaporating. You evaporate the H2S and separate H2S from water. Then what we do, we send water to waste water treatment plant, where we treat the water. We cleaned all the impurities, the hydrocarbons. We also treat it biologically. And then we send water to, let's say, Caspian Sea. Or we don't have it in Azerbaijan, in Baku. We have wastewater treatment plant, but we don't have reverse osmosis. If you have reverse osmosis, you can also use it as a drinkable water. And then what we do with this H2S? Can anyone answer me? We separated H2S from water, then what we should do with H2S? Just you can say what you think. It might be correct or wrong.
Maybe sent to the closed sulfur plant as other gas.
Yes, exactly. Thank you for your answer. As I showed here, we have H2S, which is sent to the sulfur recovery unit or sulfur production unit. So it is sent to SRU. We have sulfur, and sulfur is sent for sales. As you can see, there is no waste at the refinery. Everything is used, everything is refined as much as possible to produce all the products you can see in blue. Methyl tertbutyl ether production unit. This is can be purchased as a chemical, or you can have the separate unit for this product. Why we need this one? MTB has research octane number of 120 or 116. This can be added to gasoline pool to have the 95 and 98 gasoline. For instance, in Baku refinery, we didn't have MTB unit. And in Baku Refinery, we produced 92 research octane number gasoline. But now, because there is a revamp project, we are now building MTB unit, and when this unit is ready, we will be able to produce the 95 gasoline as well.
Sanon Bey, could you please say what is research of number? What does it stand for?
So there are octane number. So it is RON research octane number. And MON, which is motor octane number. So between RON and MON, there is around, let's say like this, delta is around 10. So research means that the theoretical octane number, which can be calculated, motor octane number is calculated with the motor or engine. For instance, in Azerbaijan, at the petroleum stations, you see RON 92 or 95. But if MON is written, then that would be 82, 85. In USA, it is written like that: RON plus MON divided by 2. Is it answer to your question?
Yes, thank you. I haven't known until now what does it mean in the stationaries, but now I caught it. Thank you.
You are welcome. And petroleum refining. So why we refine oil? To produce these products, starting from gases to bitumen and asphalt. And we will have the preheating, we will have the side products, we will have the single column. This is the single column crude distillation column. And then after we separate all the products, then we send it to them, the rectifying the columns or the stabilizers. Now we will talk about this in detail. So as you can see, the products starting from off gas to vacuum residue have the boiling points of this one. End point, it's also written like end boiling point. So naphtha has end boiling point of 180. Then the kerosene 240. Then you can also think like that. Naphtha, we have the initial boiling point and end boiling point. Naphtha has initial boiling point of around 30. End boiling point is 180. Then kerosene has 180 to 240. And then light diesel 240, 340, and so on. So kerosene means that kerosene is not a pure substance, it's also a mixture. But kerosene has such hydrocarbons that when you boil them, they will start to boil at 180 degrees, and all the kerosene will be evaporated when you have the temperature of 240 degrees. This continues like that. And then you can also see that specific gravity also increases, starting from 0.6 to nearly 1. The water, you know, water specific gravity is 1. And crude oil is around it can be different. We discussed it in previous session that the crude oil can have the different specific gravities. There can be light crude oils or heavy crude oils, but in Baku refinery we have around this 0.875. So it is somewhere here in between atmospheric gas oil and vacuum gas oil. When you separate the light products from the heavy products, the density distribution seems like this one. But we also discussed in previous session that naphtha, kerosene, and diesel. These are the products are called the transportation fuels, which add the most contribution to profit. That's why you always try to produce as much as naphtha, kerosene, and diesel, especially naphtha and diesel, because you cannot play with the kerosene amount. It is what it is in the crude oil, but you can play with the naphtha and diesel amounts. That's why you try to produce these fuels as much as possible to earn more money. Crude oil distillation. Crude oil starts from here. We have atmospheric distillation, we have vacuum distillation, and then this is the different view of the BFD again. We will talk about the subsessions. Again, 1, 2, 3, 4. What is 1? Crude oil storage. We have crude oil storage here. It is sent to furnace. This is the furnace. 2. It is sent to CDU. This is the crude. That's the atmospheric distillation unit. ADU, I will write like that. And then fractional distillation. Then vacuum flashing. It is vacuum flashing. These are your products. These are sent to different units. Crude oil distillation. You can see the distillation column at the right hand side. We have the primary separation processes and secondary conversion processes. Secondary conversion processes, which we talk about in the next session, will be FCC, will be CCR, will be ISO, DCU, BBU, etc. The conversion of some of the hydrocarbons into products having higher quality performance. So what we said that we want to produce more transportation oils. For instance, FCC, we have the vacuum gas oil, which is the product from vacuum, heavy product. Go back. This is the vacuum gas oil. You crack vacuum gas oil in FCC to naphtha and diesel. Atmospheric and vacuum distillation of crude oils is the main primary separation process. So, CDU and VDU are physical processes. Because we only separate the products. There is no conversion, no chemical reaction there. This is the crude atmospheric distillation unit. So, as I said in the previous session, that the crude oil consists of the 100 compounds and more, and we have to separate them for their based on their boiling points. So starting from 30 to 180, this is naphtha or gasoline. From 180 to 260, you can see the different boiling points in different photos because they are from different references. In previous one, it was 240, now it is 260, but this is okay. It depends on the spec, product spec, what you want to achieve. This is kerosene or jet fuel. Then you have diesel, fuel oil, lubricating oil, and residue. And the most important part in crude oil distillation part, also in the refinery, is heat recovery. As you can see, it says a preheated crude oil is sent to fired heater. Then we have this temperature around 400 degrees Celsius. It is sent to crude oil distillation tower. Here it is flashed, stripped, and we separate the products: gas, naphtha, kerosene, light fuel oil, heavy fuel oil. These can also be called as diesel, and residue. Residue to where? To vacuum distillation unit. Pretreatment of crude oil. So crude oil comes from the ground, which contains variety of substances such as gases, water, dirt, and mineral. As you can see, this is the crude oil. But this is also crude oil with emulsion. This is sand, water, and I will call it pure crude oil. Of course, the water content is not that high in the crude oil, but this is just illustration for you that how it can be separated. Once you add the demulsifier to make emulsions, then once you make the emulsions, you can separate it in, let's say, three-phase separator. Why you pre-treat the crude oil? Because to prevent falling and corrosion in the subsequent operations. You don't want to damage your equipment. That's why it is first pre-treated, then it is further processed. So I add this slide that when I send the presentation to you, you can read it. I just want to skip this part because we have much more to talk about in the process side. Crude desalting. Go back to here. Before it is sent to fired heater, we have desalter here. The question to you, why we need to desalting crude? Why we cannot just send it to distillation tower immediately? Any idea?
Because inside the, let's say, crude oil, we have chloride salts, or let's say some impurities. That's why we need to dissolve it, because then it will affect the corrosion in the pipelines.
Yes, exactly. Thank you. So the salt can deposit inside the tubes of the furnaces. So your answer was one of the let's say 3 or 4 possible answers. Salts deposit inside the tubes because you know that inside the heat exchangers we have small diameter tubes. Diameter can be around maybe 5 millimeter or 10. So these are small. There's salt deposit inside the tubes of the furnaces and on the tube boundaries of heat exchange. They can deposit here. So that will decrease your heat transfer efficiency. This creates a falling. This can result in corrosion. And also, this is also really important. The salts carried with the product act as catalyst poisons in catalytic cracking unit. So catalytic cracking, it is FCC. FCC, chemical process. It is chemical process, so it has the catalyst because it is fluidized catalytic cracking. And this salt can poison the catalyst. Catalyst is expensive, and also it really determines how process is going on. If the catalyst is poisoned, then you have to shut down the whole refinery, remove the catalyst, renew it, which costs a lot. Okay, I will explain the process like here. We have the crude coming and we add washed water here. The question to you, why we add washed water? We don't want water in the crude.
Because
Yes, please.
we need to create some sea level for increasing our sea level. Then we separate our salt from the oil.
Not exactly. Do you have it? Does anyone has another idea? So it is dissolving. There is something relationship between salt and water.
Water, salts can be dissolved in water easily. Maybe we
Yeah.
separate them by dissolving salts in the water.
Yes, exactly. So this is the more correct answer. We add washed water to dissolve the salt first, and then once the salt is dissolved in the water, we can separate it with water. We use the electrodes here to separate the water and the crude. We have baffles or deflectors here, and this is the crude collector. The salted crude leaves from top and water leaves from bottom. What kind of chemicals should we also add here to make the water crude interface clearer or better interface? What kind of chemical to create the emulsion here?
Maybe surfactant.
Surfactant is more about the interfacial, but
Yes,
here we add the demulsifier. Surfactant is used to control the surface tension of the liquid, but here we need demulsifier. Why? Going back here. You can wait for a long time for 1 hour, then you will see, you will get this one. But demulsifier helps you to create the emulsion in a short time. That's why we add the demulsifier. Let's say in 1 minute, you can create this emulsion. Once you have this emulsion, it is easier to separate the oil and water. Even the emulsifier is not added here. It is added before crude is mixed with water. Here you can see it is says that water crude emulsion. And then the commercial crude salt content is around the 10 to 20 ppb. What is ppb?
Parts per billion.
Yeah. So it is 1000 ppm. What is ppm?
Parts per million.
Yeah, exactly. So then 1 ppm, how many percentage is it?
10 to the minus.
There are two types of desalting, single, multi-stage. Single desalting is not used mostly because it is not enough to clean all the salts until the desired level. So refiners aim at 5 ppb. This number is so low. That's why most of the time we use the two-stage desalters. Two-stage desalting is required. A high degree of salt removal is desired. 95-99% removal of the dissolved salt in the crude oil. So stage of desalting, we first heat, we mix and settle down. It is heated to 130-140 degrees in the train of the heat exchanger. And then we mix. Single-stage desalting with water recycle is usually justified if salt content in crude less than 40 ppb. So if it is less than 40 ppb, then we use a single stage. But if it is higher, then we use the double stage. Double stage desalting is also better for residuum hydrotreating. In later stages, it is better for hydrotreating. In this case, the fuel oil quality is better. As I told you, we form the emulsion of crude and water, and then we separate the salt dissolved in water. I think, yes. These are the dissolters. You can see in the photo, both of them are dissolters. And the operating variables in desalting, the crude charge rate, temperature and pressure, mixing valve pressure drop. Where is the mixing valve? Do you remember? Where do you think that there can be mixing valve? You see here mixer. So we have heated crude oil. We add the emulsifier here. And then we add water and we have mixing valve. Most of the time it is static mixing valve that helps to mix the crude and water. Wash water rate and temperature, wash quality and desalting voltage. We have the electrodes. It is electrostatic desalter. That's why the voltage is also important here. This is another photo of the desalter, which you can see the inside of the desalter. We have the high voltage insulators, upper line electrodes, crude oil outlet, process pressure vessel, and where is water outlet? It is not shown. We have water inlet, crude inlet. The water outlet is not shown here. So this is the PFD of the desalter. So typically two-stage desalters are used. We have the unrefined crude. We have the water, which comes from the second stage. And we have mixing valve electrodes per stage. We have the wash process water. And process water is added to the, let's say, second stage. We use the recycled water in the first stage. Do you know why, or any idea why we do that? We could also do the vice versa. Use the processed water, fresh water in the first stage, and then use the recycled water from first stage in the second stage. Why we don't do that, but we do this way?
Maybe if we would first add it to the first line, more salt will be dissolved. Salt dissolved in water. Water wouldn't be such useful for the dissolving process. But if we add it in the second stage, less salt will be dissolved. So it is not doymamış məhlul əmələ gəlir sanki.
Yes.
Və biz yenə həll eləyə bilərik. Yenə
Yes.
duz həll eləyə bilərik.
Yes. Thank you for your answer. That is the one point. Another point is that I am interested in this desalted crude. So this is my spec. Let's say 2 ppb. And that's why this crude, the product from the second stage, is much more important for me. That's why I'm using the fresh water in the second stage to make sure that I can separate or I can dissolve all the salts. And then, as you said, from the second stage, we already have the less salt because of the first stage. We can use the recycled water in the first stage. And then the desalted crude is sent to distillation tower. furnace and pre-flash. Most of the time we have furnaces before the distillation columns because we need to achieve the temperature, desired temperature first. Let's say here it's around the 400 degrees. To achieve this one, we need the furnace. But we also pre-flash. Pre-flash can be like this one. So this is, as you can see, we have the furnace, and then it is sent to column. But let's say this is the main column. I can add here pre-flash column. Why do you think I need this one? What do you understand when you hear pre-flash? So, pre-flash means that the separating gases from the stream. I have main stream here. So pre-flash. I can separate the gases here. And then I have liquid here, which can be sent to furnace. Then I do not have this one. It helps me to separate the gases, and I heat lower amount of feed into the main column. This way I can reduce the power or the required fuel of my furnace. That's why we can use the pre-flash column. Now I will talk about the burners. The preheated crude from the preheater section is further heated and partially vaporized in the furnace containing tubular heater. This is the tubular. You can see the tubes here. They have a kind of a circle like that, so that for the most efficient heater. So the furnaces has two zones. The main zone here, where you have the burners, all the fire, this is called the radiant section. But after this one, this is the main part. This is the second part, is convection section. Convection section. How we can use the convection section for heating? Do you have any idea? Okay, so for burners we use the fuel gas. It can be C1, C2, sometimes even the C3, C4, the LPG is used. And we need air, of course. We need oxygen. These are around the 25 degrees, ambient temperature, 25 degrees. But once they are burned, they leave the radiant section as flue gases. What are flue gases? What type of gases in the flue gases? Who can tell me? What's the composition of flue gases? Okay, I will tell you. So air is oxygen and nitrogen. The fuel gas, let's say it is hydrocarbon. Then when carbon is burnt, we have the CO2. When hydrogen is burned, we have H2O. Oxygen we use for burning, and we have nitrogen. This gases has around temperature of, I don't know, up to 200 degrees Celsius, even higher. And you have hot flue gases, the gases. Then you can add some more tubes here. In convection section, you use the heat from the flue gases to heat your other streams. Even you can produce here steam you have water inlet, and because of the high temperature, it leaves as the steam. And then your flue gases leaves the convection section at the 120 Celsius. So all the furnaces have two sections, radiant section and convection section. In radiant section, you have the burner's main fire, where you have the main heating area of the tubes, and these tubes leave the furnaces. But in the convection section, you can heat the streams that has lower temperatures. Now this is the part of the pre-flash column where you have feed, you have flash zone, you have the wash oil slope marks, which are the different products. In our case, we will have the kerosene, we will have the naphtha, etc. This over there has a function of providing liquid wash to the vapors going up the column from the flash zone. So here, vapor goes up, and you have the liquid comes down. The overflash provides the heat input to the column in excess to that needed to distill the overhead products. You can see that you have here this distillation column, which we will talk about in detail later. Here, separate the naphtha, kerosene, diesel, the atmospheric gas oil, and residue. But also, it is really important to control the outlet temperature, furnace outlet temperature, to keep cooking inside the furnace tubes, and also avoid cooking in the column flash zone to a minimum. You don't want to have lower temperature, because if you have a lower temperature, then you have poorer distillation. But you don't want really higher temperature, then you might have the cooking, or you can have the cracking that you want to prevent. The composition of the crude plays a part in determining the maximum temperature allowed. Why? Because we know that we have the light crude and we have heavy crude. That's why this temperature can be different for each type of crude. For instance, the also composition of the crude can be different. The paraffinic, I mean the content of some crude are more paraffinic, some crude are more aromatic, etc. Paraffinic crude oil cracks more readily than an aromatic or asphalt-based crude. In this case, you have the lower temperature to prevent the cracking of the paraffinic crude oil. Furnace and pre-flash, these are the furnaces, and these are the stack. You can see the flue gases go up from here, and then leaves the furnace in the stack to the atmosphere. The heavy refraction of the crude oil leaves from the bottom section of the pre-flash tower, and both streams have higher, lighter. I want to skip these parts and talk about the heat exchanger network.
I'm so sorry. Yes, I have a question. Could you please go back to the previous slides, which was cooking? Yes, cooking.
This one?
Cooking, the previous one.
This one. I have cooking here.
Yes. Keep cooking inside the furnace tubes. This cooking is the such refinery process unit, or the cooking in the heater. The problem, let's say, in the heater.
The cooking is process. Here we call
This
like
process,
a process, which actually you are right. We have also DCU, which is the delayed cooker unit. So what we do in DCU, we have a special reactor and we produce coke. Coke is like, I don't know, stone, or in the reactor it becomes like a stone, then we, with high pressure steam, we crack it down to like sand, coke. So, but what happens in the furnace tube is that we have coking. So let's say if we have coking here solid hydrocarbon formation here, it is formed here. It is really like a stone, and then this reduces heat efficiency, and then you can also have problem if this becomes bigger and bigger, then there is no way for your fluid to pass it through. Did I answer your question, or your question was?
Yes,
Okay.
it's clear. I asked the second one.
This coking is kind of similar to this coking, but here we have the special reactor and we want to produce coke. But in other units, we want to prevent coking. Who has an idea what is HEN, or heat exchanger network? Heat exchanger network, kind of the network of a number of heat exchangers, 6, 8, 10, etc. As you can see, we have two heat exchanger network in crude distillation. One before the desalter and the second after the desalter. The crude comes, let's say, around 225 degrees Celsius. And then, if you remember, who remembers the temperature we need for the desalter? At least you can say what you remember. 130. So we use what we use here. Okay, I will continue, and then it lives around the same the degree Celsius, the desalter, and we have the heat exchanger network 2, and then furnace to pre-flash column. From pre-flash column we have the main column. We can use the pre-flash column the before furnace or after the furnace, but in this case we have the gases here and liquid here. It helps us for better distillation. After the furnace, we know that it is 400 degrees Celsius. Before the furnace, it is around 280 degrees Celsius. We use the lighter products such as the naphtha and kerosene in order to heat crude oil in the first preheating train. This is called the preheating train. Train 1, and this is the second one. We have the cold crude oil. We want to heat it, preheat it, and we use the lighter products to heat crude oil. We also cool down the lighter products. Later we will see that after this, naphtha and kerosene is sent to air coolers and the coolers, the water coolers, to cool them until the desired temperature. We use the heavier products because heavier products have also higher specific gravity and they have the higher heat. We use the heavier products to preheat crude to the furnace inlet temperature. We use HGO. You can see the dashed lines. LGO is light gas oil. HGO is heavy gas oil. Gas oil is diesel, light diesel, heavy diesel, and residue. A question, assume we don't have HEN2, what will happen?
Can I ask a question before
Yes, sir.
before your
Sure.
question? So if we want to increase the temperature to 130 degree in the dissolved, let's say operating temperature, so can we use only one heat exchanger? Because I think it will be more cost effective than the heat exchanger network.
So if you want to use the one heat exchanger, that exchanger will be so big, first of all. Okay, all the heat exchanger will have the same size because the crude passes through all of them. But you don't have so much heat in one stream. Where you will take that one? Because why it passes through different heat exchangers? Because the heat exchanger duty is limited. You know that Q
and we will
Q
share
is
this duty in 2 or 3 heat exchangers, it means.
yes, exactly. So Q, the heat exchanger duty is mass flow rate times specific heat times delta temperature. And this is limited for each, let's say, naphtha mass flow rate is limited. Kerosene is limited. And CP is specific for each. You cannot do anything for CP. That's why you cannot have only one heat exchanger because then this heat duty will not be enough. That's why you have a couple of heat exchangers. You can see that the first you have lightest product, naphtha. The second you have the heavier product, kerosene. Here again, the first you have the lightest product, light diesel. Second is the pump around, we will talk about later. Heavy gas oil, and then finally you have the residue. Because you increase the temperature, you need more heat duty to increase it more. That's why, and this heat duty comes from the heavier products.
And what about the how much, let's say, temperature is recommendable to increase in one heat exchanger in terms of industry, let's say?
There is no such limitation. The outlet temperature is not what you calculate, it is your result. And for heat exchange network, you can design what is important is heat recovery, the percentage of heat recovery. If you can recover 90%, that is really good. It means that for the rest 10%, or you use the coolers, water coolers, or you use the heaters. It means that you can use the 90% of the heat in your unit, but for the 10%, you have to use the cooling water or fuel gas as heater. This is important. And if you have, let's say, 1 to 3 heat exchangers, you can even make the best heat exchanger network. In design course, people do that even at Baku Higher Oil School or the other engineering universities. But if you have many heat exchangers, then you probably need the simulation such as the Aspen HYSYS to have the best heat exchanging network. It decides which streams you should have heat exchanged. But there is no such a limitation that this should be the maximum delta temperature for the heat exchanger. Okay?
Yes, it's clear.
Okay. Then let's come back to my question. If you don't have hand 2, what will be?
We would need to increase the furnace load, or
Yes,
for example, we
exactly.
need some.
Yeah. Continue.
For example, we need some components at high temperature to give it to the furnace, burning and creating heating process. But if we heat it beforehand, we will need lower load.
Exactly. Exact answer. I will not add anything here. Thank you very much for your answer. Let's continue. This is heat exchange.
Sorry, and can I
Yes.
ask a question?
Yes, sure.
We also use the heat of the residue, but the residue has high, for example, high thickness. It is. I thought it is hard to move it through pipelines. How we can use its heat in the heat exchanger? Isn't hard to use its heat to move it through pipelines to the heat exchanger then?
So thank you for your question. To answer your question, I will go back. So vacuum residue has higher density, and you are the you are right that it is hard to move the not vacuum residue, it was atmospheric residue, not shown here. Atmospheric residue, I will write AR, is around 0.9. And if it is the high viscous or the too hard to move in the pipeline, we most of the time add steam there to move them. However, it has also high temperature. One moment, sorry. I lost my pen. I'm sorry for the disturbance. I have to. My PowerPoint slide stopped working. Try to solve it. So atmospheric residue has a specific gravity of 0.9. You are right that it is hard to move the atmospheric residue or higher the density products in the pipelines, but we also have to consider that they have the temperature of the around 400 degrees Celsius or even more. So when the temperature is higher, this helps lower viscosity. So with lower viscosity, we can easily move them in the pipelines. If we have the temperature goes down below 100 Celsius, then we will have a problem to move them in the pipelines. Sometimes it happens that they see that it can be dried or to just kind of the make solid. It happens to act like a solid. That's why they add steam in this case. Did I answer your question?
Yes, thank you.
Thank you for your question. So now it is the heat exchanger network. You can see that crude is sent to heat exchangers parallelly with two pumps, and these are the products that we use in heat exchangers. This is hand 1, and as you can see, the heat is transferred from hot product, jet fuel, gas oil, kerosene, etc., to crude oil, and then we also cool down these products. After the heat exchangers, we have the air coolers or even the water coolers to bring the products to the desired temperature at the battery limit. And then it is sent to desalting. After desalting, we have the N2. Here we have only two heat exchangers, but it can be different for different systems. And how your system will look like, this is done by pinch analysis. You will learn, I think, in your design course. And then heat exchanger network. As I told you, for more heat exchangers, the Aspen HYSYS is really useful to make this network for most heat recovery. I will skip this one and CD video. So we have the first heat exchanger network, we have the salting, we have the second heat exchanger network, then we have the furnace, and then we have here crude oil enters the atmospheric distillation unit at around 400 degrees Celsius. This is 720 already. So the crude oil distillation consists of atmospheric and vacuum distillation. And atmospheric distillation, as I told you, they have these products. And then we have the AR, atmospheric residue, which is also sent to furnace to heat it more. And then we have the vacuum distillation. LVGO is light and heavy vacuum gas oil. Okay, what we do with LVGO and HVGO? Where it is sent? Who remembers? It is sent to fluid catalytic cracking unit to crack them down to produce more transportation fuels. We said that we have preheating, we said we desalting, furnace, pre-flash. We have pre-flash in some of the units, but we don't have in others. So that's why it is optional. We have distillation column. This is the overview of the products, where you can see that you have the temperature, EIBP, initial boiling point, and final boiling point, or atmospheric column, and then we have the vacuum column. The CDU main column is typically 50-meter high. This is the CDU, and this is the VDU. And it has around 30 to 50 valve trays. Crude is fed at the lower point. Crude is fed around here. And from here you have the atmospheric residue. This is the flash zone. This is the stripping zone. And then we have the side strippers as well. It is above what's called the stripping section. Heating inside vapor flow high rate requires large diameter column above the flashing zone. Above flashing zone here, you need a large diameter. At the bottom of the stripping section, steam is injected. Why steam is injected? We have steam here. Why? Because it will strip the atmospheric residue of any lighter carbon. What we want to do, our aim is to separate transportation fuels as much as possible from heavy residue. What are the transportation fuels? Naphtha or gasoline. We have jet fuel. And we have diesel or gas oil. I will continue more quickly because it is already 7:30. I want to finish this presentation, but the slides I skip, you can read them later and ask me your questions via email or in the next session. We have side strippers and we have pump arounds. Why we need pump arounds? You can see we have 1, 2, 3, 4, 5. Pump arounds help us to control the temperature. We can control the temperature here and control the temperature here, 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 and here. As you can see, we take the product here, kerosene product. This is the side stripper, 1, 2, 3, and then some of the kerosene is sent back to the column. This helps to control the temperature here. Why we need this one? Because for kerosene, let's say we have the 180, 0.40. This is our spec. We want to achieve this one. And these are the cuts, if you remember. To achieve this one, we need to control the temperature. And this is reflux. So you cool the naphtha, and then some of them leaves as a product, and the rest is sent to the top of the column to control the temperature there. And it applies the same to pump around 4 and 5. And bottom one, as you can see, we don't have a reboiler here. Atmospheric residue is directly sent to vacuum distillation. These pump arounds have the, I think, yes, when the heat exchanger symbol is gray like this, it's a part of crude oil preheat exchangers. As you can see, these heat exchangers are part of the heat exchanger network here. We preheat the crude oil heat exchanger, and these side streams, we add steam here to strip the lighter products. Let's say we have the kerosene here. What is the lighter product is naphtha. Where is it? Yes, naphtha. If there is naphtha left in the kerosene, we can strip it with steam. If kerosene is left in light gas oil, we strip it with steam, and so on. All of these products are withdrawn above their feed tray. So here it is withdrawn, here it is withdrawn, and here it is withdrawn. The atmospheric residue is withdrawn from the bottom. So this is the atmospheric residue where it is withdrawn. This is the block flow diagram. We discussed it before. And then the products from the atmospheric distillation is sent to other units. Most of the time you can also see like the SR, straight run, straight run naphtha. Straight run means that directly from CDU. So you can call this one SR naphtha, SR kerosene, SR diesel, SR gas oil, SRGO. I will skip this one because we don't have much time for this one. So what is it about briefly? Fractionation is done based on the boiling points. And we have a light cut here, we have heavy cut here. So if we have a gap between light cut and heavy cut, that is perfect. That's perfect for us. It means that it starts from 30, ends at 180, and we have 180, 240. This is the naphtha. This is the kerosene. If you can do that, this is perfect, but that is not nearly possible to do the perfectly. What we have 30 here. We have the 185 here, 175 here, and 245 here. Then you can see that in naphtha, we have kerosene left. The gap between 185 and 180 is kerosene. And we have also naphtha in kerosene. So how you determine that one? You have kind of spec, what you should be your aim, what is okay for you, and based on this, you design your distillation column. If you want to have the perfect distillation, you might have ended up the distillation column with more than 100 trays. The CDU pressure. So CDU column is controlled by the back pressure of the overhead reflux drum. Where is it? Yes, here, this one. You can see that it is 2 atm, which is equal to 1 bar G. And this is the overhead reflux drum. This is the pressure of the 0.3 bar G. This is where you control the CDU overhead pressure. The top tray pressure is 0.4, 0.7 bar G. And the flash zone, this is, by the way, is video in the photo, not CDU. How I know that, I will tell you later. The flash zone pressure is usually 0.34, 0.54 bar higher than the top tray. So here, the here top tray P plus 0.34, 0.54 bar. So if it is, let's say, the 0.7, this is 0.5. In the end, we will have the 1.2. It's a bit high. Probably it will not be the case. Maximum is 1 bar G. The overhead temperature, again, is around the 15, 20 at the top and 450, 550 in the bottoms. And the bottom is sent to vacuum residue. Top is sent to where? Top is sent to overhead reflux drum. We have here 15, 30 degree Celsius. One moment, please, one moment. I'm so sorry. And then we separate the gases here. So what we don't want. So in gases, let's say there is maximum C5 spec in gases around 2 weight percent. What does it mean? In gases, we make the analysis, and then out of the analysis, we have the result. There should be maximum of C5, 2%. If we have 3%, it means that we are losing naphtha or gasoline in the gases. What we should do, we should decrease the temperature. Decrease the temperature to liquefy the naphtha or increase pressure. That's why it is always desired to have the highest pressure at the top as much as possible and lower temperature. Also, we have to consider the C4 spec in naphtha. If it is also more than enough, then you need to decrease the temperature to evaporate the LPG to remove at gas. the flow rate and capacity. So the capacity of refinery is equal to capacity of CDU. So because all the crude comes to crude distillation unit first, and then it is that the product are sent to different units. For instance, it can be said that the capacity is 6 mmTA. It means that million metric ton annum. It means that the capacity of the refinery is to refine 6 million metric ton crude per annum. And the crude column is typically designed for 80% loading, and which means that we have the 20% gap. The capacity of the column is limited by the vapor flow rate with a velocity of between the 0.8 and 1 millimeter per second, which means that we have vapor here, and until here it will have the around 1 meter per second. For instance, if you need the residence time of the 1 minute, your column height will be 60 meters. The vapor flow rate increases as the vapors rise from the flash zone to the overhead. Crude oil is coming here. This is the flash zone. It starts to evaporate, and of course, the vapor flow rate increases. To keep the vapor velocity within this limit, we have the pump-arounds, which we talked about, which are installed at the several points. So previously, we had the 1 reflux and 3 pump-arounds. To expand the crude capacity, we may add the pre-flash column. So what pre-flash column does? We have the pre-flash column. It takes the bottom of the pre-flash column as crude oil to CDU, and gases like from let's say middle of the column. This helps us to increase the capacity of the distillation column. Stabilizer section. Naphtha we have here, but this naphtha is unstabilized. Who can tell me what is unstabilized? Unstabilized naphtha means that we have gases in naphtha. So gases such mostly LPG plus naphtha. Stabilizing means that we are sending it to stabilizing column, and we are separating the liquid naphtha from gases, LPG. Of course, we have here reflux drum. I didn't draw it. We have here reboiler, like a typical distillation column. So we assume this is the stabilizing section. We have the gases here, and we cool it down. We have air cooler. We have reflux drum, and again we separate the LPG as liquid and send the rest of LPG back to column. And from bottom we have the liquid naphtha, and liquid naphtha is sent to NS. It is a naphtha splitter, and we separate the liquid light naphtha. Who can tell me where light naphtha and heavy naphtha are routed? Light naphtha is used to is routed to isomerization unit. Heavy naphtha is routed to continuous catalytic reforming unit. This is the stabilizer section. We have the light naphtha. Most of the time we have the heavy naphtha. We don't have medium naphtha at Baku refinery, but you may find it in different refineries. The CDU pump arounds, I talked about the pump arounds, saying that we have the pump around 1, 2, 3, 4, and you can also count reflux as pump around. My question to you, why we need pump arounds?
I think, for example, we have higher pressure inside the trays and lower pressure between the reflux, and we have pressure gradient, and to overcome this gradient, we need to pump it from low pressure to high pressure.
Okay, that's clear. We want to send the liquid. It leaves from here. We need to send it back to column, and for this we need pump, because otherwise, as you can see, we want to send from lower point to higher point. We need pump. But in general, why we need to have pump around? What would be if we don't have it? We don't have pump around. I don't need it. Can I say this one? What's the purpose of pump around? The purpose is, I also said it before, to control temperature. To control temperature at different locations. I want to control temperature here. I want to control temperature here, here, here. Why? Why? Because these are the points where I extract my product. My product is extracted from here. My product is extracted from here. From here. That's why these are important points for me to control the temperature. For instance, reflux. If I have the, let's say, naphtha in gas, it means that I am stripping naphtha. I have to cool the tower overhead to save naphtha. I don't want naphtha to leave as a gas. That's what we do. Increase the reflux, and then decrease the temperature at tower overhead, so that we don't let naphtha leave as gas. These are all show the pump arounds and heat exchanger network. Usually 2 pump arounds up to 3 are used in conventional designs for crude distillation units.
Sanbay, can I ask one question? So
yes,
quick.
Sure.
We can put the pump around only after the distillation columns, or before or after the distillation columns, and in the other sides of the plant we cannot.
I mean, in all distillation columns or stabilizing columns, you can have pump arounds. Pump around. Thank you for the question. Actually, that is where I want to explain it. This is the, let's say, the distillation column. So what we do, we take it, let's say, from 13th tray. We have this one. We have heat exchanger. We have pump. We pump it to 14th or 15th tray. It is 120 degrees Celsius. From heat exchanger, it is 100 Celsius. And then we kind of control the temperature. We cool down the 15th tray with this pump around. Exactly, it is happening here. The main column consists of 45 trays. The secondary columns consists of 4 trays each. These are the size stripper. Size stripper 1, 2, 3. For kerosene product, for light gas oil product, for heavy gas oil product. The main column has 2 sections that are distinguished with respect to the flash zone. Okay, these are the flash zone. 4 trays, 4 trays are the flash zone. This is the flash zone. And 41 trays above the flash zone. The bottommost tray is numbered as 1. This is 1, and we go up. So trays 13, 22. 13, 22. LGO draw of tray. On 10 trays above the HGO processing zone, process the LGO product portion of the crude. From tray 22, withdrawal of product is taken and sent to LGO side stripper. LGO is sent to side stripper. Another liquid stream is taken out and sent to tray 24. You can see here, this is pump around. We have heat exchanger here, and colder LGO stream is sent back to above 24. So it cools down. If we see that we need to cool down the temperature at 24, we increase the flow rate of this pump around. And basically, when the temperature at 24 decreases, all the temperatures below this tray starts to decrease. So we basically control the temperature between 13 and 22 with the flow rate of this pump around. And it applies the same for others. With this pump around, we have no pump around here because we save here less energy than gaining. We use more energy for pump around, but it does not affect more. However, we have pump around here. Again, that we control the temperature of these trays with this pump around. Is this clear? Or if you have any question, please ask here.
Yes, it's totally clear.
Okay. So because we have the similar slides, I will skip them. You can read them later. Vacuum distillation column. Okay. Just 3 minutes. I will finish vacuum distillation column. I know it is already iftar time in Baku. So in vacuum distillation column, we have packing, 1 packing, 2nd packing, 3rd packing, and this is VDU, and this is the vacuum generation package. You can see this one. These are 2. These are the vacuum generation package, and this is CDU. Here, our main products are VGO, vacuum gas oil. We can have soap and vacuum residue. Vacuum residue is sent to VBU and DCU. And we have the vacuum system. We have the steam ejectors, as you can see. Steam can be used as ejector, or we can use the diesel product. We can have sometimes the diesel product here, and we can use it in the ejectors to create the vacuum condition here. And the vacuum condition is around 30-50 mmHg. Vacuum overview. As you can see, we have the accumulator here for atmospheric distillation, and this is the VDU. We have the LVGO, HVGO, and VR as products. As I told you, sometimes we have the diesel here, but the flow rate of diesel is low. This is shows a steam vacuum generation package. We have the ejectors at the top of the column. You can see these are the steam ejector package tubing, which helps to create the vacuum. You can see the ejectors here. I want to talk about more, but we don't have enough time. We can discuss it in the next session, and I will also send the slides so that you can review and read them. This is the end of presentation. If you have any questions, please ask.
I believe we don't have any more questions because it's already iftar time. So thank you very much for presentation and especially the presentation, Sanam Bey. I believe each of us learned a lot today from you, and we'll have additional session with you on Sunday.
Yes.
Thank you very much once again, and dear participants, thank you again, and have a good day.
Have a good day. Have a nice iftar for those who are fasting.
Okay.
Bye.